Okay, thanks a lot for coming here. So what we are planning to talk about today is that there is a root of trust, security, various types of server platforms that we see in the world, and how, because it's a so much dynamic nature, how the FPGA can help to achieve the server security. And there's two presenters here.
Hi guys, good morning and welcome to our session, how to leverage FPGA-based root of trust for securing the platforms, especially focused on attestation. I'm Mamta Gupta, Senior Director Marketing at Lattice Semiconductor. I run the security, data center, and telecom BU, so very, very closely associated with the solution and the ideas that we are going to present today. I'm going to hand over to Munir for now. He'll take us through the agenda, and then I'll step in for some of the expert comments in the middle. Munir.
So hi, yeah, so this is Munir Ahmad. So let me go through what we have today. So the first I want to talk a little bit about system architecture, and we are seeing so many differences in system architecture. And then what is that we're seeing? There's reference measurement, attestation, and all those things, and the need of attestation. And then from there, I like to draw a conclusion that because of those so many variations of things we're seeing, we need something that is programmable or variable attestation entity or verification entity. And then overall system security, attestation is just one single piece of that system security. And then obviously we do the PFR, platform firmware resiliency, which is part of the total security. And then there is different ways of attestation. We talk about a little bit on that. So let me take to the next slide. So this is the slide that we're showing that there's so many different kinds of architecture that we see, right? Obviously you see the DCSCM, which is a favorite from OCP. Then you have one level above up, which is DCMHS. And then you have IPU, Intelligent Processing Unit. You have edge computing. You have a storage server, enterprise servers, OEM servers, and all those things. And also there's some application-specific servers that we see. So architecture is so different. It's very difficult to come up with this unified method of attestation, especially when you have so many different protocols. You have new definition architectures coming, new way of interfaces coming. So it's very difficult to sometimes. So that's what we still think that FPGA is a better place. So at the end of the day, you need to have someone as a verification entity that can do attestation of the devices that you're running on all of our different ways of doing things. So let me take to the next slide. So this slide talks about device reference integrity measurement. So what it is about is that if you look at, there is various levels in the manufacturing process. Obviously, you have a manufacturer who gives you the devices, could be CPU, could be memory, could be anything else. So they have their hardware, but then also they have the binaries, policies, memory content, all those things to put there today, right? And then obviously there can be entity to do the verification that can run those measurements, policy checking, and all those things. But things get even complicated more because in that whole time, you also have some upgrade, right? You have life cycle management stuff that you want to do. And also there can be a new security requirement that the old security requirement may be obsolete, right? So fixing all those things, and then definitely the critical one that we're saying, that certificates, SPDM measurement. There's various ways of defining those things. SPDM is one of them that they're talking about today, but there's some other protocols that run the security measurement. So defining all those things and putting this all together in orchestration device or verification device could be very difficult if you just have a very, very hard architecture like that. And by nature, FPGA is a soft architecture, right? You can define, it's a programmable architecture. So if you have, let's assume that you have a new requirement coming from CNSA, it's easy to implement in an FPGA rather than changing the whole hardware. You can do a field upgrade, right? Anytime you have a new firmware upgrade, you can do the new attestation measurement. It's easy to do in the FPGA based. So the next slide is that, so it's kind of like, we want to talk about what is the need for attestation of a system, right? We know, but truly what this need is that a system or device should be able to provide is trustworthiness, right? That's the whole thing here. And what I mean by that is firmware is running good, its hardware is running good, and then also the access capability of this one. You may not have you may not want every component of the system to have a full access to the system itself, right? You can have a policy based on what component of the system can access what. So all this thing is a very complicated scenario. It's not just something plug and play you can do. There should be a manifest, there should be a programmable content of this, and that's what we see the need for attestation of the system. And there is various entity today. They're doing very fantastic job. You see TCG is running that, CISA. You have also NIST compliance, the FIPS compliance. So there is various entity is trying to tackle the problem security-wise, because security landscape is not just one thing. It's many things together, right? You have runtime configuration, you have boot time configuration, you have firmware changes, you can have policy changes based on who is doing what. So all these things is verifying, mandating, all those things is managing by several committees, right? And if you look under the right side, just wanted to make attention there that there is a graph there just want to show. This graph is showing up to 2023. I don't know if you can see the year here. It's very small in my screen, but it's showing the firmware attack. It's actually growing over the year. The more and more servers you are seeing, more and more remote management capability that we are adding, obviously the hacker is getting more and more on that one. And on the bottom, NIST is trying to define some of the critical components of the system. So I just wrote down that now the critical component is something that is, even we see that today the fan is even a critical component, because someone can go to hold of fan and can actually do the denial of service, right? Because if you somehow hack fan firmware, if fan doesn't run as it should be, the server cannot run, right? It's going to overheat and it's going to stop running. Okay. So the whole thing that we are talking about is so many variations that we see in the server space, so many new architecture that we're seeing. It's very difficult for a system designer or a system architect when he designed the system to fully comprehend the security landscape, the vulnerability they're facing, and then new firmware upgrade that needs to change, new security hack that they may see. It's very difficult, right? It's almost impossible to see the future today, especially when you have so many hacking activities, so many people are working on those things too. So in a secure platform, we know that there is things that we like to define too, right? It's not only that a system needs to divide the proof of verifying entity, so you have a verification entity, and you have a device that's giving the attestation, attestation measurements and all those things. But it's not only during the boot time, it also during the runtime. There is also changes happens continuously in the BMC space, the configuration and all those changes. So we need to have those things also thought through properly, that yes, it's not only boot time configuration, the runtime. Most of the attack we see actually the runtime configuration changes, right? People can go and do runtime what it is needs to be done. So bottom line here, if you want to do predictably design something that is a long served, and you don't have to remove the hardware from the system in service, I think FPGA could be an ideal choice because of this programmability. And then if you see something that is already hacked, if you see some thread, then yes, FPGA can work on that. So FPGA can offer basically the control invocation, immutability. We do have immutability, and also the measurement diversity. So you don't have to stick to one measurement. If there is a PQC requirement today that is coming that needs a different kind of measurement, you don't have to stick to that. You can always change this on the fly because it's a programmable entity in the FPGA. So with that, I'm going to hand it to Mamta.
So thank you, Munir. So Munir touched upon a lot of key concepts here where we are talking about establishing trust in the system. We are talking about actually a zero trust system, which might sound a little bit oxymoronish that, hey, we are talking security, why are we talking zero trust? Zero trust means I don't trust anybody. Every component has to prove its papers or show me their papers, not only from the hardware perspective, but also from a software perspective. So that was the whole point about attestation and establishing zero trust in the system. Now, systems are so diverse, as Munir touched upon, so many architectures. How do you predict the zero trust requirements for those? That's where reprogrammability is your friend. Now, to have a zero trust environment, to have a diverse a solution that services diverse systems, you need some cornerstones. You need to have something that will give you assurance that, yes, this is the right solution for me. So some of the security cornerstones that we talk about in our FPGA world are like platform firmware security. That has come up in last 3 to 4 years very heavily, because now this protect, detect, recover, backed by that NIST 800-193 guideline, is becoming ubiquitous. You know, a lot of people are adopting it in one form or the other, and this is what is needed to start the trust in the system. That I have a secure boot, I have an element that can boot securely, I will then have runtime protection for myself, and if I get hacked, it's actually no longer if, with all the firmware attacks that Munir was talking about, it's when you get attacked, then I should be able to recover myself. So we are talking cyber resiliency. So that is a key component of establishing trust in a system, that I trust this system. Not only that it will protect itself, it will also recover itself. So that's the ethos of PFR. And then what do you need to do that chain of trust? So there's another concept called chain of trust in a zero trust system. You need to start from a foundation of trust. There has to be an immutable identity sitting at the bottom, giving you trusted elements that you can bubble up and say, yes, I'm now building a chain of trust on that. So you definitely need a root of trust for attestation, for any kind of trust establishment in the system. Now, currently, all our systems are running on classical asymmetric crypto. You're all familiar with them, RSA, ECC, and all of that is now under threat with post-quantum computing. So they will be like paper to a bullet. So it's not like, hey, I'm using ECC 256 today, I'll go to 384 or 512, and I'll be safe. No, it's paper to a bullet. You have one sheet of paper or 3 sheets of paper, doesn't matter. So quantum computers, due to there's something called Shor's algorithm, they can break the classical crypto, asymmetric crypto today. So we have now a new guideline from United States government. It's the commercial arm of NSA called CNSA 2.0. A lot of you are actually following CNSA 1.0 without actually realizing it. So whenever you are using ECC 384 in your systems, you are following CNSA 1.0. Now we are transitioning to CNSA 2.0. For servers, it is 2025. In 2025, you need to have post-quantum algorithms as default and preferred. So I always do this as a public service announcement. Go check it out. CNSA 2.0 guidelines for servers. So what does that mean? That means whatever system you are setting up for zero trust implementation must be post-quantum aware. It should be post-quantum ready. So again, as Munir said, these security requirements are going to morph. They're going to evolve. And one thing to note is these post-quantum algorithms are a very new kind of a math. It has not been time tested. So the whole industry that is involved in this post-quantum math is aware that this math can be broken. And we started with like 16 candidate algorithms. We are at like 2 now, because rest of them were broken. So the industry expects that when you will implement a post-quantum aware algorithm, there is a good chance that it can be broken and you may need to upgrade it. How do you upgrade it? If you have already solidified this in a silicon, how do you upgrade it? That's where FPGAs come to rescue. They're reprogrammable. You can actually upgrade the algorithm. Now, the fourth cornerstone is, okay, secure boot. Everybody is aware that I need to boot up securely. I need to authenticate what I'm booting, and it needs to be encrypted if it needs to be encrypted. But what happens during runtime? Your SoC is running, it's taking firmware. Who's keeping a check on that SoC? That whatever firmware it is running, at runtime, it is secure, or it is expected. That is where we are proposing a lot of new innovations where we are implementing BMC on FPGAs. We are part of many such industry efforts. We are part of OCP's High Performance Computing Group, where we are contributing to the soft BMC, where we have now desegregated, or we are proposing to desegregate the SoC element of BMC and the secure element of BMC, so that the secure element can still keep a watch on the BMC. So it is now a put-together system which is runtime secure. So those are the 4 cornerstones that you need to keep in mind. You have to protect yourself, and you have to recover from an attack. You have to have a root of trust where you can build a chain of trust. And then you need to be quantum aware and prepare for churn in that application. And then you need to have some solution for runtime security for a secure element like BMC in your system.
Yeah, I think our time is up, right?
Yeah, OK. So I talked about platform firmware resiliency. So we had, and also we talked about the root of trust for attestation. With this, I'll give to Munir to wrap it up. And thank you. Yep,
thank you. So I think this is just one way of showing how we can use the BMC as a bridge for the root of trust attestation, because BMC has hooked to the system, many portions of the system. So there is not a significant changes in the platform architecture that is needed. I know my time is up, so I'm just going to wrap it up. We have a lot of these demos in our booth in the A36, and so please come join us. We also have a demo in server innovation and Oran Villas. So with that, I'd like to conclude the session. Thanks a lot for all of you to be here. Thank you.